Hello, everybody. Welcome back to undergraduate seminar. I'm very excited to have Maitreyo come and speak with us. He reached out. He's at IACS Kolkata. I'm glad we could connect. And he's going to tell us about the Toeplitz Conjecture. Please take it away, Maitreyo.
Thank you very much. I want to thank the organizers for giving me this wonderful opportunity. So I am Maitreyo Bhattacharjee. I'm an undergraduate student at IACS Kolkata from India. And today I will be speaking about the very famous open problem in geometry and topology. It's known as the Toeplitz Conjecture. Okay. So at first I would like to thank the organizers for giving me this platform. I am very much grateful to the Mathematical Association of America, the Indian Mathematical Society, and my institute library for giving me access to numerous resources like books and magazines, which have been extremely valuable for me from time to time. And of course, thanks to my parents for everything and the support. And of course, these slides are available from my webpage. And after my talk, we'll also send my slides to the organizer who can just post it on the webpage of the talk series as well. I want to dedicate this talk to the memory of Professor Yuri Ivanovich Manin, and many of you may know that he was one of the greatest mathematicians of the second half of the last century. He sadly passed away on the 7th of January, if I'm not wrong. And I actually got the news after a couple of days. And Yuri Manin is known for a number of reasons. He has done extremely notable work in the fields of algebraic geometry, mathematical physics, number theory. And in fact, if you go through the YouTube, the list of talks he has given, his titles range across an incredibly broad range of topics. And they range from both pure disciplines of mathematics as well as cosmology, physics, and all those stuff. So yeah, and most importantly, he has produced a number of very brilliant students who are still active in research. Most notable among them are Professor Vladimir Drinfeld, who won a Fields Medal for his work in Langland's program, and of course, Professor Alexander Belinson. So his death is surely a big loss to the mathematical community worldwide. Okay, let's begin. So here is a brief outline of the talk. So at first, I will be briefly recapping some geometric and some topological concepts, which are mostly known to any undergraduate first-year topology student or even a mature high school student. And then I will focus on the statement of the problem. And perhaps the most striking feature of the problem so far has been the existence of many partial results. Now, the existence of partial results without the complete proof of a problem is not new in mathematics. It has been there for a long time, and it happens for a number of problems. But the thing about this problem, which especially attracted my attention at first, was that the nature of the partial results is quite unique as compared to other problems. Means that the number of possible cases in which the problem which could have been proved without solving the problem in its full generality is huge. And I will try to cover a number of cases in this talk of mine today, and I hope you will enjoy it. And towards the end, I will also discuss some variations and generalizations of the problem into various settings. Like when we are talking about geometry, you must be wondering about what happens when we go a few dimensions above our usual, let's say, Euclidean plane or the Euclidean space. So I will try to highlight some of that. And of course, I will end by listing some references which I've used when preparing the talk, and also not only some paper references, but also some extremely nice video expositions on the problem, which has been recorded and is available publicly on YouTube so that the interested people can view them. Okay, so let's begin. So at first, what is a Jordan curve? So Camillo Jordan is, of course, a very famous German mathematician about which many of you may perhaps have heard. And the Jordan curve is eponymous on his name. And it is a very useful concept both in mathematics as well as various topics in physics. So Jordan curve is nothing else but a simple closed curve. And I'm sure that every one of you must be knowing the definition of what a curve is. It is basically a projection of an interval, let's say AB onto R2, the Euclidean plane. If it does not cross, so Jordan curve is a special subclass of a curve. So Jordan curve is a curve which does not cross itself and has no endpoint, meaning that it somehow starts, that every point is a kind of starting point for the curve. So if you want to imagine the scenario, you can imagine the picture of a circle. So when you consider a circle, you cannot particularly specify any point to be the starting point of the circle. you can just start from any point and just come again back to the point by a periodic movement. And so you can just deform the circle into any ways, and that's what is meant by the definition and the terms which I've used here. S1, of course, denotes the unit sphere, and R2 the Euclidean plane over here. So any topological embedding, and whatever that means, is basically a Jordan curve. And if it does have any loopholes or structures, something like that, then we will not classify that as a Jordan curve. And so relating to the Jordan curve, there is this very famous, and it is a theorem, of course, is a very, very famous result, which is extremely, I will say, easy and trivial to observe, but proving it rigorously in a mathematical sense is quite difficult. And so it goes by the name of the Jordan curve theorem. It says that every planar simple and closed curve in R2 divides the plane into an interior region and into an exterior region. So by this picture below here, I am highlighting what I am exactly meaning by an interior and an exterior region. Over here, you can see that the ellipse is a Jordan curve, and the region inside that, the inside region, we define it as an interior region, and the area outside, the region outside that is known as a exterior region. In fact, so easy to observe it is often believed that there are many professional mathematicians even today who are not very much familiar with the rigorous proof of the theorem. So this is the case, but it's a bit difficult to prove it mathematically. And it was Veblen, Oswald Veblen, who gave the first proof. Veblen is a very well-known name in the field of geometry and topology. A prize known as the Oswald Veblen Prize is given in his honor every 3 years for important contributions made to the field. So this was the basic definition of the Jordan curve. It's quite centrally important to the rest of the talk because the statement of the conjecture itself rests upon these special kinds of curves. Yeah. So before delving right into the problem statement, I would also consider some families of curves which would be of crucial importance, the reason which I will tell a bit later. So what is a polygonal chain? So we are all familiar with straight lines. So imagine a family of straight lines. Do not confuse it with the vector space in which you study in the usual linear algebra class. These things are much simpler than that. So if you consider a family of straight lines such that they are connected in a form of line segments, then the total curve which they form are known as a polygonal chain. In the mathematical literature, they are also known as piecewise linear curve. And the term piecewise will be highlighted in a more precise manner in the next slide. So it basically says that if you take this particular curve, then you get some kind of discretized nature in the curve. There's some absence of continuity in the sense that it's not similar to that of, let's say, a circle or any arc which you consider. It is made up of small line segments. And another very important class of curves, it is known as the locally monotone curves. So we all read about monotone functions in our mathematical analysis course, which says that if fx is a real defined monotonic function, then if x is greater than y, then fx is always greater than fy. In this case, we are restricting that monotone behavior from the global part of the curve to a local part. So the curve is locally monotone if for all points which are on the curve, there is a neighborhood of points and a direction specific to that neighborhood, which I have explicitly mentioned as ny. So no chord of the curve in the neighborhood is parallel to ny. If you just visualize the picture of what I'm trying to say, you will be very easily able to see that locally monotone does not mean that the curve is monotone in its strictest sense in the entire domain of its definition. But if you consider every point that is on the curve, then this monotone condition will hold as good. And it is also a very direct observation that all polygon curves are indeed closed convex curves. Yeah, this is what I was actually meaning by piecewise defined function, and they are also known by the name of hybrid functions. It's a function which is composed of a multiple subfunctions, and which basically means that function is the definition, the interval of definition of the function is broken down into a number of subintervals, and each subinterval is necessarily defined by a separate function. And so you can see that in the figure in which I have considered in my talk, so each interval has a separate color. And the separate color is actually is signified by very different specific functions. And over here, I considered the case of linear functions, which means that in each interval, the function is defined in a straight line way. You can also consider more extreme examples where the curve is linear somewhere and then it's continuous in some other domain, etc. and etc. But this specific kind of curve will be very important for our discussions, and that's why it demanded a separate, let's say, separate discussion. Okay. So what is the statement of the conjecture? So it is a very easy to state and possibly understand, but I don't know, perhaps, and that's why I have put a question mark over there, but an extremely difficult conjecture in topology. And also, although it has been solved for some special cases, assuming various smoothness condition. Now, smoothness condition is a very analytic definition. So smoothness, as you can guess, is linked to the differentiability of the curve. Now, it is not necessarily when you are taking a curve in R2, it's differentiable everywhere where it is defined and all these and all these. So this is what is actually meant by general curves. But when you are talking about the conjecture, you mostly focus on the curves which are smooth. And we mostly vary the degree of smoothness. That is, sometimes when the earlier works were done on the curve, they considered curves with which were mostly smooth. And it is widely believed that it is easier to prove the conjecture. Actually, not widely believed, it has been shown mathematically that it is easier to prove the conjecture when the conditions are more smooth, implies the curve is more, let's say, differentiable in many manners, and it is discretized. By discretized, it can also be piecewise linear, as I discussed in my previous slide, but in its full generality, which means when a curve is discrete in some region, continuous in another, so on and so forth, there can be numerous such examples. The problem is still open, it has not been solved, and in fact, widely open. It is also believed that general topological methods may eventually fail in solving the problem. These are, although in fact, speculations, there have no evident reason for believing all these, but it is believed by many mathematicians that many new kinds of techniques will be required for solving the problem in its full generality. And this is not entirely false, because every time an important special case has been solved for the problem, there have been multiple number of new techniques introduced which were totally absent from the literature previously, and the setting for the problem has changed over the century. So it was first stated by Toeplitz in 1911, and the question basically asks that every simple plane closed curve in the Euclidean plane has an inscribed square or not. And so here is Toeplitz, and some of you may know him for his famous eponymous Toeplitz matrix in function analysis, which is very frequently used. And here is a basic diagram for the conjecture. So here you take a Jordan curve, and you can see by what I am meaning by simple, plane, and closed. It is closed in the strictest sense of the term, and it is planar because it's not consisting of any volume or something, as an inscribed square. And now one needs to be a bit specific about the word inscribed over here, because as you see in the picture, when we are considering 4 vertices of the square, they all lie on the curve on which we are considering. By inscribed, we do not necessarily mean that the square has to entirely lie in the region which is inscribed by the whole curve, because that may give you counterexamples. And as you can easily see, out of, I guess, even the 4 examples considered over here, only one is almost entirely within the region of the curve. Usually, by inscription, we mean that the figure must be entirely contained within the area of the curve, which is actually false for this particular conjecture. With the assumption of such strong conditions, the problem does not necessarily hold true. But if you relax that condition, that's the main premise of the conjecture. And let us see what is known on that. Yeah, I basically made this slide after doing a further literature study on the problem. So though it originally belongs to the domain of geometry and topology, the ideas which are involved in solving the problem have heavily relied on tools and theories from other fields of mathematics, for example, analysis and combinatorics. And so the main thing over here is that the mathematical object, the curve with which we are dealing with over here, can be handled more in terms of analytic function than geometric and topologic manner. I mean, is that the general tools in geometric topology, in that of some of the people may have taken a basic algebraic topology course where they study the concepts of homology and cohomology. So these kind of tools do repeatedly come up in solving the problem for some cases, but it is often surprisingly striking that for many cases that approach generally fails. And it is also believed that in the final proof of the problem, more than topological method, a number of geometric methods must be used. So by meaning that it lies at the crossroad of so many areas, I want to say that not only is like no one particular field will be useful in proving the problem in its full generality, but fields as diverse as combinatorics and analysis, and these were actually introduced into the premise of the problem quite recently, I would say, in the last 10 years. And there is also a field known as metric geometry, about which is not, I will say, a very standard course taught in undergraduate classes, but it's a very useful field in research, especially in computational and discrete geometry, which was used very recently to solve an important class of problems. So as you can see, that is an extremely interdisciplinary problem and demands tools from many fields of mathematics. Okay. So after seeing that problem, one can easily approach to solve the problem by a technique which one learns in one's first analysis course. Maybe like approaching to solve the problem to first establish it for well-behaved curves. By well-behaved, you can easily guess that I mean differentiable and smooth curves. By showing in some manner that well-behaved curves have inscribed squares, and then take any arbitrary square in the plane, arbitrary curve in that plane, and approximate that curve using the smooth curve for which the conjecture was already proved. And this approach actually helps, and it actually helped some earlier mathematicians who worked on the problem. But later it was found that due to some geometric and topological reasoning, particularly some which I have discussed in the slide, that the inscribed square which you are considering for the problem, when you take it as a limit of sequences of curves, it, instead of being a square of non-zero area, it may just squeeze to a point. So it may, the scenario may not be mathematically valid if you always use this kind of argument. And instead, various other kinds of tools are required for proving the problem in this generality. So if you take the limit of a sequence of inscribed squares, in the general situation, the limit may go to something kind of zero object, where it may have squeezed down to a point. And so that will not be a valid proof. Yeah. Okay. So first we consider some initial cases. And it is very easy to observe that, of course, squares, if you take squares and circles, so they have infinitely many inscribed squares, and this is very easy to show, in fact. And yeah, so things get a bit complicated for triangles, which are, let's say, one vertex, one side less than that of squares. Yeah, so this is the case for the triangles. So acute angles have extrably 3 inscribed squares, right angles have 2, and obtuse angle triangles have exactly 1. And this result was established by Bailey and in the Mathematics magazine in 1998. And the result is a bit tricky and uses some certain complicated geometric tools. It is also not very difficult to prove that if you consider curves which are symmetric about the origin, then they will definitely contain one inscribed square. And the proof can be considered as an important, an interesting exercise. And the hint for that will be that it involves some rotation argument of the plane about the symmetric curve which one considers originally. Okay. And also it is an easy observation that parabola, which is a very important class of curves, does not admit any inscribed square due to a similar reason. As you can see, parabola has the nature of branching outwards. And if you take any 2 vertices on the parabola, it is very much impossible for you to get any 2 other vertices which are on the curve, and the 4 vertices will form a square. They can indeed form a trapezium at maximum, but it is impossible to form a square in that case. Yeah. Okay. So these are the results which Yeah. So parabolas are not Jordan curves. Actually, yeah, parabolas cannot be considered as Jordan curves, but I have just mentioned as a side details, of course, they are not Jordan curves. So when we are dealing with Jordan curves, they have to be closed kind of objects. So I'm just actually, while for mentioning a few initial cases I had considered for the triangles and rectangles and for the circles. So that's why I had considered the case for the parabolas also. Yeah, so thanks for pointing that out. Okay. So Toeplitz, while stating the problem, came to have a proof of it. And as we know that this practice is not uncommon among mathematicians and who are familiar with the, of course, the very famous Fermat's last theorem know that Fermat had made a very similar claim for convex curves. Although in this case, never claimed of having a proof for the general setup, he claimed for a proof in the convex curve case, but his proof was never published actually. And for the same case, works of mathematician Emke and Zindler later led to a complete proof, which was published in 1921 for the case of convex curves. In 1916, proved it for piecewise analytic curves. So what are piecewise analytic curves? So as I had discussed previously, piecewise curves are curves which are, of course, defined on subintervals and so on and so forth. And if they are analytic in nature, means that they are quite well behaved in some mathematical sense. And if they are defined piecewisely, then the Toeplitz conjecture holds. That means one can get an inscribed square among that. So this was established by Emke in 1916, and Emke was actually an invited speaker in the ICM also, and he was a person who did extensive work on this problem in the much earlier years. So I will discuss a few of the history in the next slide. And he mostly contributed to a lot of results, and he himself had found results which he did not realize implied by some of his earlier works. Like he had published 2 papers on this topic, one in 1916 and one in 1918, if I'm not wrong. So some of his results in 1918's paper could have directly followed from that of his 1916 original paper. Okay. Mathematician Schnirelman proved the conjecture for C2 curves. And by C2, of course, I here mean that continuous and twice differentiable curves in the usual sense of the manner. From Quest in 1989. So you can see the difference of the years. It's 1944 and 1989, almost half a century. So like almost 45 years. Proved it for locally monotonic curves. And I discussed previously a few slides back of what exactly are locally monotonic curves. And his approach was more analytic in nature, I would say, than a geometric and topologic approach. And it established some new techniques which were used later by other mathematicians to study the problem. And it was a quite useful approach, I would say. Yeah. Nielsen and Wright, a few years later, proved the conjecture for curves with reflective symmetry across lines. Like if you take a line in the plane and you take such a curve that if you reflect it across the line, you get the same portion of the curve. So there's kind of local symmetry present in the curve. So for that, the Toeplitz conjecture holds. And this was established by Nielsen and Wright in 1995. And yeah, that was a breakthrough at that time. And this was followed by another results of Maitreyo in 2011. And the name Maitreyo will again reappear in the talk because he basically wrote a 2014 article in the Notices of the American Mathematical Society, which was a beautiful survey of the problem, including numerous special cases, techniques, further conjectures to explore. And it is one of the best references to be explored if one is interested in the problem. And in his PhD thesis in 2011, he proved the Toeplitz conjecture for some special classes of curves with a particular restriction that it does not contain special trapezoids. So whenever I talk of restrictions, it basically means that we are, in some sense, deviating from the general condition of a curve, and we are considering curves with predefined properties of analytic nature, and we are doing all those works on that particular class of curves, and then we are in some way hoping of extending that problem to other class of curves. So that was the work of Maitreyo in 2011 when he proved the conjecture for this class of curves. And 3 years later, Cantarella, Dene, and McCleary proved it for C1 class of curves, meaning for continuous and differentiable class of curves, of course, Jordan curve. Yeah. So the latest, perhaps the latest result which one has in this field is by Greg Chambers, who is currently a professor at Rice University, that he proved that Jordan curves, in some sense, which are close to twice continuously differentiable Jordan curves, have satisfied this particular conjecture. And I have not specially elaborated on the what posed over here, but if you go through the paper, it's on archive. I don't know whether it has been published or not. By closed, he particularly considers some metric geometric arguments to take. Yeah. Oh, great. Yeah. So he particularly considers some metric geometric arguments involving some epsilon to establish the conjecture. It's a very beautiful result. And in fact, it is the latest major results in this area. And so we have not seen much advancement after this particular result of Chambers. And it involves tools from both combinatorics as well as analysis. And this truly highlights the on the crossroads philosophy of the problem, which I had discussed a few slides back. Okay. Yeah. Just a second. Yeah. So let us go back to the beginning of 1913. So it was then when Emck had first proved the problem for smooth enough convex curves, and his proof for the piecewise analytic case, which he had published 3 years later, were in fact a consequence of some rotation of second arguments, which he was considering while solving the problem. That while if you consider any random point of the curve, and if you consider some seconds, and if you rotate them, then something remains invariant, which leads to the existence of squares inscribed in the curve. And in fact, I would go as far as to say that he was able to prove that there are an odd number of curves inscribed, or odd number of squares inscribed inside the curve. And there are some deep reasons to believe that most of the times there are odd number of squares inscribed in the curve instead of even number. And it has also come up in the works of many other people. And there is a very interesting historical anecdote over here. He was basically informed of this problem not by Toeplitz himself, but by the mathematician Kempner. Okay. So the work of Schnirelmann in 1929, where he proved for the locally monotone case, there were actually a few errors. And by error, this was not originally realized by Schnirelmann when the result was published. And as far as I know, he was made aware of this by a few people later, and it took him quite a bit while to correct the work. And it was actually later published post his death in the year 1944. But there, if you read the survey of Matske, you will see that there were still people who claimed that even after the publication of the correct result, that some results were not quite viable in the second paper as well. Okay, so this was mostly 50 to 60 years back. Now I will be focusing on this era and the number of techniques and tools which have been used in proving this problem over the last 10 or 12 years. Most interestingly, and I will confess over here that I myself got to know about this result quite late. It is there in the survey paper that there has been computational approach apart from geometric and topologic arguments to prove this particular conjecture. And one of the most prominent ones in this direction is by Peterson, Verberg, and Osterrad, who published in 1913 the following result, that if you take a Jordan curve, a 12 by 12 square, then that particular Jordan curve will inscribe a square, and we could also give an upper bound on the size of the square, which is 1 by root 2 times the size of the largest axis parallel square that fits into the interior of the curve. So you see, though I had earlier said that the interior argument is not very much needed for the original statement of the conjecture, but as you see that more days go, a number of techniques come into the play, and though techniques most of the times open up a huge areas for mathematics to explore, it also sometimes leads to some kind of obstructions. And by obstructions, I mean this kind of obstructions, like over here, the computer investigation could not deal while establishing the conjecture for in general all configurations, but they had to restrict themselves to some interior condition. And personally, I have not gone through their proof in details, but I felt that it's a really interesting result, which is worth discussing. And there can also be a viable approach in proving the conjecture in whole generality using a computer in the future if someone comes up with an argument of this kind, like this. Okay. So now, in 2017, Maitreyo established the conjecture for a particular class of curves, and here we will see in which curves does he talk about. So we basically proved that the Toeplitz conjecture is true if our curve gamma is a union of two Lipschitz graphs of Lipschitz constant which are less than equal to 1 by epsilon, and epsilon is a positive number over here. So I will not state what a Lipschitz graph is. It can easily be obtained in a Google search. But those who know, they can easily visualize the figure that if we consider two particular Lipschitz graphs, Lipschitz continuity is in fact a stronger condition than normal continuity, and the condition on epsilon, I'm sorry, I forgot to explicitly state over here, is that epsilon has to be something positive. And given a Lipschitz curve and given a particular Lipschitz constant, if you just kind of glue the ends of the Lipschitz curves together and you allow to vary the Lipschitz curve in the middle, then tau proves that the Toeplitz conjecture is valid. In fact, that we can find a particular square. And his basic approach was by fixing the four vertices of the square in terms of these coordinates, which you can easily see explicitly depends on time. So here basically gamma 1, gamma 2, gamma 3, and gamma 4 are the four vertices of the square, and x, y are the basic components, and the time actually all of them are time varying. And in his proof, the curve actually, the square form depends on the time, and the explicit dependence are also described by t, bt, and their plus and minus. And actually the plus and minus factor come over here due to when we are shifting from one curve to another. Like in his proof, he considers the vertices of the square when, let's say, two of them may be on one Lipschitz graph and another two may be on another Lipschitz graph. And that's why the plus and minus AT-BT factor emerge in the proof. And also there is a bit of combinatorial argument at the end of the proof. And the main thing it deals with is the area under the rectifiable curve, which is given by this particular expression. And some of whom you may have taken an advanced know that this is a differential one form. And we are taking the area which is described in this particular region, T0 to T1. And in his paper and also a subsequent talk which he gave at CIRM Martial, he also considered a weaker version of the problem known as the periodic square peg problem. Due to the limitation of the time, I will not be able to discuss the periodic problem, I think the restricted problem in full details, but it is generally believed that if the period, like the whole solving the whole conjecture will help in this is the periodic square peg problem is a weaker version than that of the original conjecture. So solving this will not necessarily imply solving the entire conjecture. And this was what proved in 2017. It was kind of nice results. It was a blend of a lot of techniques, but still it did not contribute, it does not solve the conjecture in its full generality. Okay. Yeah. So now we have talked a lot about squares. So now what happens in the case of a rectangle? So we know that the square is basically a special case of a rectangle when you have all the four sides equal instead of two sides being equal to each other. So for any given particular rectangle, so actually for all rectangles, we can define the aspect ratio to be the ratio of its longest side to the shortest side. So we are just assigning a certain measure to the rectangle. And it was proved in 1981 by Vaughan. And it was a beautiful argument that every continuous Jordan curve has an inscribed rectangle. Now, the main argument used in his proof is that he considers the Z2 group acting on the torus, which is nothing else but S1 cross S1. And it basically permutes the two coordinates of points present on the Jordan curve to any, and these 2 points may be random. There is no restriction on choosing the points. And then the quotient space is nothing else but the very famous Mobius strip with which we are all familiar with. So in 1981, this was the result of Vaughan, and this actually opened up and lead to advancements in a lot of areas. Many further works were also done based on this particular technique. But of course, it did not cover the problem in one particular case, which is that if you take a rectangle with any arbitrary aspect ratio, then you could not guarantee that there will be, then it will be inscribed inside a Jordan curve. So this particular part of the problem was open, but at that time in 1981, it was a major advancement. And later, actually much later, in 2019, Hugelmeyer, who was at that time a doctoral student at Princeton, who is, I think, currently a postdoc at Stanford, refined his arguments and covered the case for rectangles with 1/3 of all possible aspect ratios. So it was a major improvement of his results. And previous to that, this result was posted on the archive in 2019. And in 2018, he had solved the case for an aspect ratio for rectangles whose aspect ratio equal to √3. It was a separate paper, and I believe the arguments were a bit different, but most of the work built upon the earlier work of Vaughan. Yeah. Finally, a breakthrough was achieved in 2020. And as you can see, this is the Quanta magazine coverage of the particular news. And during the lockdown of the COVID-19, Joshua Green, who is at Boston College, who is also famous for other reasons, because one of our students, Lisa Piccirillo, solved the very famous problem that not every Conway knot is a slice. So he's a very famous mathematician in this community. And his colleague, Andrew Loeb, proved the rectangular peg problem in its full generality, meaning that if you go to the abstract of their paper, you will see that they mention that given any rectangle with any aspect ratio, there exists a rectangle similar to that particular rectangle, which is inscribed inside a Jordan curve. So this was a very powerful result of them. And the main factor over here is that the proof, of course, required a lot of new geometric ideas, and it basically builds upon the work of both Vaughan as well as that of Hugelmeyer. And some knowledge of advanced mathematical areas like metric geometry and symplectic geometry, which is again a very advanced area, is needed to understand the problem in its full generality. And it also deals with something known as Lagrangian embeddings and Klein-Bottle. Klein-Bottle, of course, is very familiar to many of the people who have taken a basic topology course, but the concept of Lagrangian embedding may not be very familiar to an undergraduate. And even I am not very much familiar with that concept. But while briefly glancing through the proof, what I basically understood is that the main innovation was forming a new geometric framework for the problem, which was earlier non-existent, but which was heavily depending on the concepts which were introduced by Vaughan in 1981, as well as Hugelmeyer, about which I talked in the previous slide back in 2019. Okay, so this was a big breakthrough about, and it solved the case for the rectangular inscribement inside a Jordan curve. And yeah, so let us now focus on some further questions. So in the year before the breakthrough work of Vaughan in 1981, so in Meyerson in 1980, the result which is similar to that of Green and Loeb for triangles. And over here, I basically highlight the word triangle because, so I have not basically defined anything which is the aspect ratio for that of a triangle, because we know the condition of similarity for triangles. And you can even for a rectangle, you can scale it up to some limits, but for the triangles, the concept of similarity is quite famous. So what Meyerson in 1981 exactly proved is that if you are given a particular triangle, then you will find a triangle which is similar to that particular triangle of yours and which is inscribed inside a Jordan curve. And yeah, so this was the kind of results. So it is quite amazing to note that the flavor of result which was proved by Green and Loeb in 2020 was actually not extremely new The reason is because Meyerson had proved similar results for triangles much earlier. I mean, almost 4 decades early. So this is the beauty of this area. Like, there are a crossroads of a number of techniques, number of ideas, number of proofs, that it's quite fascinating that the idea or innovation used by one person may be extremely useful for another person a number of years later, and it comes back in strange and mysterious ways. And his work was actually extended about a decade later by Nielsen, who proved that the set of all these inscribed triangles is dense in some sense. And so that was also not advancement towards the code conjecture, but a very, I will say, a major advancement towards one version of the problem when we are considering triangles. So till now, we mainly dealt with existence problem. Like, we were interested if at all there exist inscribed squares or not. Seems that the opposite question can also be that the number of inscribed square in some Jordan curves in various classes of curves, and by various classes I mean that they must be Jordan curves, and that the prescription on them can vary, like they can be of some different analytic behavior or something like that. So we can quantify things and talk about the number of embedded squares in particular Jordan curves, and there has also been works in this direction. So at first, Vasilev in 2008 explicitly gave the construction of smooth convex curves, and by convex, I'm sure that many of you will be knowing the definition of convex. It says that if you take any 2 points in the interior of it and if you join it, it lies entirely within that. And convex analysis and optimization is an extremely huge area in mathematics, both in pure as well as applied. It also intersects a lot with computer science and a lot of other things in this field. Okay, so Vasilev basically gave the construction of some smooth convex curves which have n number of squares, where n is any assigned number integer. So his result was actually quite influential and powerful, and this led to, again, a number of advancements, both in the case of curves as the smooth convex Jordan curves, as well as in some other cases about which I will be talking in a while. So 3 years later, Sagos and Marin in 2011 proved the same. I mean, they gave an explicit construction for inscribed squares, n inscribed square, where n is any pre-assigned integer for piecewise linear curves. We of course could not extend to the full generality of Jordan curves, because that question is of course much more difficult, but they could handle the case for piecewise linear curves in 2011. And this particular person, Van Heest, about whom I read in the survey paper, he in his master's thesis deals with this particular question in the case of algebraic curves of degree D. Now, the case of algebraic curves is especially important and interesting here is that whenever we talk about algebraic curves, that many a times it deals into questions concerning algebraic geometry. And so, though I have not read his master's thesis exactly, what he basically proved is that for like, if you take the degree of the algebraic curve as D, then he gave an explicit quadratic formula for the number of inscribed squares which were possible. And like, there were two cases. In one case, those many number of inscribed squares were possible, and in other case, infinitely many of them were possible. I do not know whether there have been further refinement of his results or not, but I am very sure that this will be an extremely fruitful area of research, especially at the intersection of algebraic geometry and topology. So, like, when we are mostly dealing with 1 or 2 dimensional surfaces, there has been a lot of generalizations of these problems to higher dimensions, but of course, I do not have much time to talk about them in details. And people have been worrying about the existence of inscribed n cube in any n-1 sphere, where I basically lift the dimension up by a number of people. And just one small thing which I want to mention over here is that while dealing with this problem in higher dimensions, the question of symmetry has also come a lot into the picture. Like, people are worried about when can the inscribed cube or the, let's say, the inscribed cube which we are inscribing inside the sphere will be symmetric about some form or not. I'm not very much well versed in the literature, but I have been aware of a number of very interesting results which are coming up in this direction. And this is, of course, a very active field of research. Okay. So now I come to the reference portion of the talk. This is the inaugural paper of Toeplitz where he proposed the conjecture. And of course, as you can see, this is not in English. Yeah. So it was published in a lot of time back. And so very recently, a nice survey of this particular problem was dealt by Richard Schwartz in this paper of his in the Bulletin of the American Mathematical Society. It goes by the title of Rectangles, Curves, and Fine Bottles. Interested people can go through that. And this is basically the paper of Rick Chambers, which I was referring to in my talk. And this is a paper of Tao, which was later published in the Journal Forum of Mathematics, where he deals with his integration approach to a square peg problem. It's a nice approach, as I previously mentioned, that it solves not only does it solve the conjecture in a particular case, but also gives rise to a number of other questions, and solving them might lead to very useful direction in solving the original conjecture in general. And this is one of the super important problems in this particular field, the survey paper by Ben Maitreyo. To understand the whole paper in its complete details, one needs to take a few advanced courses in mathematics. But of course, like it can also be enjoyed by people who are like beginning undergraduates or even advanced high school students. So it was published in 2014. And of course, this is another very beautiful paper by this person, Paraj Mukherjee, who is also in the audience, who he had done a summer project on this particular problem. And he wrote a report on that, which is available from his LinkedIn profile, which I have quoted over here. And finally, this is a paper of Green and Loeb, where they deal with the rectangular version of the square peg problem. And this was archived in the May of 2020, and where the particular important version of the problem was considered. And yeah, so apart from the papers, something innovative which I want to do in this talk is that I also want to give some references to videos and pictures. So for a first-hand introduction to the problem, there is a video by none else but 3 Blue and 1 Brown on the channel. It goes by the name of Who Cares About Topology. I exactly do not remember whether this was posted before or after the pandemic. So people interested can always go and see this video. And the picture of mine in the triangle, in the slide where I considered the triangles, was taken from this particular magazine by Herbert and De Temple. This paper of them I had also quoted in my slide. And of course, there is a talk by Tao in which he had given at CIRM, where he talks about his integration approach to the Toeplitz Square Peg problem. Though the talk is not very much in details, which means that he does not cover the whole of his approach, but just gives a brief overview of what are the main techniques involved. And very, very recently, I also came across another talk on the same topic, which was given by Cole Hugelmeier. And this was given, I think, when he was a student at Princeton, at a conference of low dimensional known as the Frontiers in Geometry and Topology Research Conference at ICTP in Trieste, Italy. And here he basically deals with the problem and some of his recent work. And a paper of him in archive is also available with a similar title. There he explicitly describes his approach on the improvements of Vaughan's work and similar topics. Yeah, I am mostly at the end of my talk, so there is a small advertisement from my side. So being an undergraduate community from the Indian Association for the Cultivation of Science in Kolkata, we organize a bi-weekly seminar series, mostly similar to that of yours, but at a much smaller scale, for dissipating of mathematical and scientific knowledge among undergraduate students all throughout the world. And also it is aimed at networking. So I very much welcome you to share your work and to give a talk in our beloved forum. You can search us on YouTube. This is our handle. Any question or queries, you can always write to this email. And this is the web page of our seminar series. If you're interested, you can go there. You can search through the details. And yeah, so in the end, I thank you for your time and attention. And if you have any questions, I will be very happy to answer them. And you can, of course, always direct them to my email. Thank you very much.
Awesome. Thank you. So we have a tradition at undergrad seminar asking people to fill out this survey. So please fill that out. We're going to take a 2-minute pause while people fill that out, and then we can ask Maitreyo some questions. That was awesome. Thank you very much. So
Thank you.
we'll stop the recording here, and then questions after these, after 2 minutes.